Hello students, this lecture is only an introduction to partial derivatives. All of we know what is ordinary derivative. If y is a function of single variable, say y equal to f of x, single variable x, then what is dy by dx or f dash x, all of we know, rate of change of y with respect to x. Y depends on only one variable x, but in practice we have function of two or more variables. For example, in practical we can see that volume is a function of both pressure and temperature. And if we want to find the rate of change of volume with respect to temperature, then what to do? Then we have to keep pressure constant. And if we want to find the rate of change of volume with respect to pressure, then what to do with temperature? We have to keep temperature constant. So this type of situation when arises, we have to think of what is partial derivative. We have to use partial derivative concept. That's why we are discussing partial derivative first, because in our first chapter of differential equation, first equation concept is exact differential equation, and to test whether a differential equation is exact or not, we need the concept of partial derivatives. That's why, and also in starting partial differential equation, there also we need the concept of partial derivatives. So that's why first we see what is partial derivative. Before that, what is function of two or more variables. So first is function of two or more variables. If to each point, first bracket x comma y, ordered pair x comma y belonging to D, what is D? D is a subset of R square. R square means R cross R, Cartesian product, R cross R, that is Euclidean plane. So to each point, first bracket x comma y in the domain D, which is a subset of R square, there corresponds a unique real number. There corresponds a unique real number U by some rule f, by some rule f, then this f is called a real valued function of two real variables x and y. To each point x comma y, there corresponds a definite real number, unique real number u by some rule f, then this rule f is called a real valued function of two real variables x and y, and we denote it by f colon d tends to symbol r, but we read it f is a function from d to r, or in general it is denoted by this symbol also, f colon r square tends to symbol r, but we read it f is a function from r square to r. Here this r means set of real numbers, bold r, set of real numbers. R cross r means xy plane, Cartesian product, such that u equal to f of xy. F is a function from r square to r, and we write u equal to f of xy. For a single variable we write y equal to fx. Here we write u equal to f of x comma y, where d is called the domain of the function f. So this is function of two variable definition. For example, if we write u equal to f of x equal to x square plus y square minus 2x plus 1. See, for every pair of real numbers x comma y, this is a definite number. X square plus y square minus 2x plus 1 is a definite real number. That's why it is a function. This rule defines a function of two variables. Similarly, if we write u equal to f of x equal to e to the power x minus y, then also it defines functions of two variables x and y. Now, if we write u equal to f of x, y, z, it is x square plus y square plus z square. Say, for every order triple x comma y comma z, for every three real numbers x, y, z, this x square plus y square plus z square is a unique real number, definite real number. That's why this defines a function of three variables x, y, z, and it is denoted by f colon r cube tends to symbol r, but we read it f is a function from r cube to r. R is the set of real numbers. R cube means Cartesian product, r cross r, that is Euclidean space, three-dimensional space. X, y, z is in space. And if the domain of this function is d is a subset of r cube, then it is also denoted by f is a function from d to r, that is f colon d tends to symbol r. So formal definition of function of three variable will be like that. If to each point, instead of here x comma y, here it will be x comma y comma z. To each point x comma y comma z belonging to d subset of r cube, instead of r square it will be r cube. There corresponds a unique real number u by some rule f. Then this f will be called a real valued function of three real variables instead of two. Three real variables is x, y, z, and it will be denoted by this symbol or this symbol, where d is the domain of the function. Okay. Now we come to the concept of partial derivatives. Let u equal to f of xy defines a function of two variables x and y, then the partial derivative of this function with respect to x at any point first bracket x comma y is denoted and defined as u suffix x or del u by del x. It is not du by dx, del u by del x, or it can be written as f small f suffix x, or it is del f by del x. All are notations, four notations. Equal to what? What is the definition? Definition is, it is a limit as delta x tends to 0 of the expression. What is the expression? F of x plus delta x comma y minus f of x comma y by delta x. This is the definition. Or this delta x we can write h, then it will be limit h tends to 0 of the expression f of x plus h comma y minus f of x comma y by h. So here h is delta x, provided the limit exists. If limit exists, then only this will be called partial derivative of f with respect to x. Here what we see that y remains constant, y is not changing, f of x plus delta x comma y minus f of x comma y. So it is only change with respect to x. So that's why this is nothing but the ordinary derivative. This partial derivative is nothing but the ordinary derivative of f with respect to x, assuming y constant. So this del u by del x or del f by del x, or can be written as f suffix x or u suffix x, is nothing but ordinary derivative of f with respect to x, assuming y constant, as if we are finding the rate of change of volume with respect to time, keeping pressure constant, like that. Similarly, partial derivative of u equal to f of xy with respect to this function with respect to y at any point x comma y is denoted and defined as u suffix y or del u by del y, f suffix y or del f by del y. These are all notations equal to limit as delta y tends to 0 of the expression f of x comma y plus delta y minus f of xy by delta y, or it is f of x comma y plus k minus f of xy by k, k tends to 0, where k means delta y, change in y. H generally we denote write for delta x, change in x. Here k is change in y. So it is what we see that here x remains same, y changes, y plus k here and y there, new value minus old value, but changes with respect to y only. So that's why and of course this will be partial derivative provided the limit exists. Limit should exist, derivative is a limit, and this is nothing but ordinary derivative of f with respect to y, assuming x constant, as if derivative of volume with respect to pressure, keeping temperature constant, like that. So del f by del y is nothing but ordinary derivative of f with respect to y, keeping x constant. So this is the concept for a function of two variables. Then we see second order partial derivatives of this function u equal to f of xy at any point xy, and there are three second order partial derivatives for this function with respect to x, with respect to y, with respect to mixture, like that we shall see. So the second order partial derivatives are denoted and defined as u xx, u suffix xx or u suffix x square, or it is actually del square u by del x square, means it is del x of del u by del x. It is not ddx, del x, del x of del u by del x, derivative of derivative. Okay, or you can use this symbol with f suffix xx or f suffix x square, or it is del square f by del x square, del square f by del x square, means del f by del x of del f by del x, derivative of derivative with respect to x, two times. But what is this in limit form? Okay, in limit form it is del x of this del f by del x, you can write f suffix x, new notation, f suffix x. Okay, and this derivative of this f suffix x, here function is not f, function is f suffix x, means function is del f by del x. So in terms of limit, it will be limit h tends to 0 f suffix x of x plus h comma y minus f suffix x of x comma y, means it is the value of the first order partial derivative at the point x plus h comma y minus value of the first order partial derivative with respect to x at the point x comma y divided by h tends to 0. So that's why it is derivative of derivative. So provided the limit exists. So this is limit form definition of del square f by del x square, del x of del f by del x. Similarly, u suffix yy or u suffix y square or del square u by del y square is what is actually del y of del u by del y. This is the second order derivative of this f or u equal to fxy with respect to y. Or in another symbol we write it f suffix y f suffix y square or del square f by del y square, means del y of del f by del y. So it is del y of f suffix y. Del f by del y can be denoted by f suffix y also. It is a function again. So it is in terms of limit is limit k tends to 0 f suffix y of x comma y plus k minus f suffix y of x comma y by k, means value of the partial derivative of f with respect to y at the point x comma y plus k minus value of the partial derivative of f with respect to y at the point x comma y by k. So this is rate of change of fy f suffix y with respect to again y. That's why it is del square f by del y square. Previous one it was rate of change of f suffix x with respect to x, means derivative of derivative. That's why it was del square f by del x square. Okay. So and of course in every time we are writing provided the limit exists. If limit does not exist, then we say that no, it is not defined partial derivative. You cannot use this notation at all. Derivative does not exist here. Now another one is u suffix xy or del square u by del x del y. This is mixed second order partial derivative, del square u by del x del y, or it is actually del x of del u by del y in terms of u notation, but u equal to f of xy. So again you can write another notation is f suffix xy. It is del square f by del x del y. It is actually del x of partial derivative with respect to x of del f by del y, partial derivative with respect of f with respect to y, derivative of derivative. So it is del x of f suffix y. Here function is partial derivative of f with respect to y. So it will be in terms of limit h tends to 0. When we find del x derivative with respect to x, we generally write limit h tends to 0. But function is here not f, function is f suffix y. So it is f suffix y of x plus h comma y minus f suffix y of x comma y by h, provided the limit exists. Here actually what we have done, it is value of partial derivative of y at the point x plus h comma y minus value of partial derivative of y at the point x comma y by h tends to 0. So it is rate of change of the function f suffix y, partial derivative with respect to y with respect to again x. That's why it is del square f by del x del y. Okay. Similarly, u suffix yx order changed is del square u by del y del x is del y of del u by del x, or with f notation it is f suffix yx del square f by del y del x. It is del y of del f by del x, means del y of f suffix x, partial derivative with respect to y of the partial derivative with respect to x function. So it is limit k tends to 0 because it is del by del y and function is f suffix x. So f suffix x at the point x comma y plus k minus, here it should be x again. Okay, it is missed x, one x is there, x, f suffix x of x comma y by k, because function is here f suffix x, partial derivative with respect to x at the point y x comma y plus k minus at partial derivative with respect to x at the point x comma y by k, provided the limit exists. So it is derivative of f suffix x with respect to y. That's why it is del square f by del y del x. In general, this changed order del square u by del x del y and del square u by del y del x are same. That is, order of partial differentiation is interchangeable, but there are functions, some functions u equal to f of xy, special case functions will be there for which del square u by del x del y not equal to del square u by del y del x. At some points, particular points, this equality may not hold. Okay, of course we shall not consider these things here, and the equality holds if second order partial derivatives are continuous functions. What is continuous function we know, but of course here is definition for two or more variables. So if second order partial derivatives means del square u by del x del y, del square u by del y del x, these are also functions. If they are continuous functions of two variables x and y, then of course the equality for this order of change of partial differentiation equality holds. Always del square u by del x del y will be del square u by del y del x if these second order partial derivatives are continuous, and in our case of course we shall always assume they are equal. Similarly, higher order partial derivatives can be denoted and defined, means here we have defined up to second order, it may be third order, say it may be del square f by del x cube, del square f by del y cube, del square f by del x del y del x, like that mixture also may be there. So these are the definition of partial derivative. Now as a note here I have mentioned f suffix x at a comma b, means del f by del x at a comma b, partial derivative of f with respect to x at the point a comma b. Here point is a comma b. Then what will be the definition in limit form? It will be f of a plus h comma b minus f of a b by h tends to 0. H means delta x. So here the point is a comma b, that's why here f of a plus h comma b minus f of a b by h we have written. If the point is x comma y, it will be f of x plus h comma y minus f of xy. Okay, so this is partial derivative with respect to x at a particular point a comma b. Similarly, partial derivative with respect to y at a particular point a comma b can be written definition in limit form. Okay, so this is partial derivative of f of xy with respect to x at the point a comma b. Now, if u is a function of three variables, say f of x comma y comma z, u is a function of three variables x, y, z, then what is del u by del x or what is del f by del x? Del u by del x means u suffix x or f suffix x means del f by del x. These are notations, same. Is what? This is derivative of this function with respect to x keeping both y and z constant. So it will be what? Limit as h tends to 0 of the expression f of x plus h comma y comma z minus f of x y z by h. See, y and z are not changing, only x changing. Change value of x, original value of x. So f of x plus h and here fx. Okay, so provided the limit exists, of course, and this is nothing but, which is nothing but the ordinary derivative of the function f with respect to x, assuming both y and z constant. So if we want to find partial derivative of u with respect to y, then we shall keep x and z constant and just we shall differentiate with respect to y. Similarly, if we want to find partial derivative with respect to z, then we shall keep x and y constant. So this is the concept for a function of three variable. Okay, notation is del u del y, del f del y, or f suffix y or u suffix y is nothing but ordinary derivative of f with respect to y, assuming x and y, x and z, sorry, it assuming x and z both constant, because it is del u by del y. And if you write del u by del z, then is nothing but ordinary derivative of f with respect to z, assuming both x and y constant. Okay, now as an example, let us see. If u equal to tan inverse y by x, means this u is a function of y by x. Now suppose we want to find del u by del x. It is not du by dx, del u by del x, partial derivative of u with respect to x. So tan inverse y by x. All of we know derivative of tan inverse x by is 1 by 1 plus x square with respect to x. So if it is tan inverse t, then derivative will be 1 by 1 plus t square. So that we have written. Partial derivative of u, this u tan inverse y by x with respect to x is 1 by 1 plus y by x square. But by chain rule, we know into derivative of this y by x. 1 by 1 plus y by x square into derivative of y by x, but with respect to x. So this is simplified, x square by x square plus y square, and derivative of y by x with respect to x. Here partial derivative del x of y by x with respect to x, y constant, so y will remain as it is. Now 1 by x, derivative of 1 by x, all of we know with respect to x is minus 1 by x square. So this del x of y by x is minus y by x square. So this is the answer. Partial derivative del u by del x. See, derivative of tan inverse y by x is 1 by 1 plus y by x square into derivative of y by x, but with respect to x, partially, keeping y constant. Okay, now if we want to find del u by del y, then again tan inverse y by x derivative will be 1 by 1 plus y by x square into derivative of y by x with respect to y this time. So derivative of y with x with respect to y will be 1 by x. Why? Because derivative of y with respect to y is 1 and x is constant. So this is the answer in this case, del u by del y. Now if we want to find del square u by del x del y, mixed second order partial derivative, then it is del x of del u by del y, and del u by del y we have calculated is x by x square plus y square. So it is del x of x by x square plus y square. So what is that? It is derivative of this function, it is x by x square plus y square. It is in the form u by b. Okay, all of you know the quotient rule for differentiation. All the rules are similar here also. So it is del x of x by x square plus y square is what? X square plus y square whole thing square, denominator square. Then denominator into derivative of numerator. Numerator is x. Derivative of x with respect to x is 1. I have written here 1 minus numerator into x is numerator here into derivative of denominator. What is denominator? X square plus y square. Derivative of x square plus y square with respect to x is twice x, because y constant here, partial derivative. Okay, so answer is y square minus x square by x square plus y square whole thing square. Similarly, if we want to find del square u by del y del x, reverse order, It is del y of del u by del x. So del y of del u by del x already we have calculated here, minus y by x square plus y square. So it is minus y by x square plus y square. But here it is del y, mean partial derivative with respect to y. So it is again quotient rule we have to apply. Minus sign let us keep here. So it is u by b for quotient form. So denominator square. Denominator into derivative of numerator. Numerator is y. Derivative of y with respect to y is 1. Minus numerator into derivative of denominator. X square plus y square. Derivative of x square plus y square with respect to y is only 2y because x here is constant. Okay. So simplifying we get this is. See, del square u by del x del y, and here it is del square u by del y del x. Both the answers are same. You can check. In our all cases they will be same, of course. So del square root by del x del y equal to del square root by del y del x. Order of differentiation interchangeable. Now, if we want to find del square root by del x square, second order derivative with respect to x, partial derivative with respect to x. So it is del x of del u by del x. And del u by del x value we have minus y by x square plus y square and del x. Now here, see, y is constant. Minus sign taken out and y also taken out, constant. Now 1 by x square plus y square. Derivative of 1 by x square plus y square we have to write only with respect to x. So it is minus 1 by x square plus y square whole thing square. All of you know derivative of 1 by t is minus 1 by t square with respect to t. So like that, minus 1 by x square plus y square whole thing square into derivative of this again x square plus y square. Chain rule with respect to x, it is twice x. So simplifying we get this answer. Similarly, we can calculate also del square root by del y square. It is del y of x by x square plus y square. X constant because differentiation with respect to y. So x taken out, and 1 by x square plus y square derivative with respect to y is minus 1 by x square plus y square whole thing square into derivative of this x square plus y square with respect to y, means only 2y because x constant here. So this is the answer. See here that del square root by del x square answer, del square root by del y square answer. Incidentally, both are same. In general they are not same. Here it is, they are same because the function is symmetrical perhaps. Okay, note, del u by del x cannot be written as delta u by delta x or du by dx. Du by dx for ordinary derivative for a function of single variable, and delta u by delta x means it is increment ratio. And if we take limit of this increment ratio, actually we get del u by del x. Okay, that's why these two symbols you cannot use for partial derivative. This is not style of writing, this is the reserved symbol for writing partial derivative, del u by del x. Okay, now change of variables in partial derivatives or chain rule of partial differentiation. For chain rule of differentiation in ordinary case, we know we have applied here also. This while finding this del by del x of this 1 by x square plus y square minus 1 by x square plus y square whole square into derivative of denominator again means twice x. So chain rule we have applied, but for partial differentiation chain rule is also there for function of two or more variables. Let us see what is that. If u equal to f of rs is a differentiable function of rns, it is a function of rns, where r itself is a function of x and y, s itself is a function of x and y, phi of xy, s is psi of xy, they are also differentiable functions of x and y. Then what is del u by del x? Ultimately u is a function of x and y. If we put the value of r, phi of xy, put the value of s, psi of xy, ultimately u is a function of x and y. So surely we can talk of del u by del x. So then the rule is that del u by del x is del u by del r into del r by del x plus del u by del s into del s by del x. This is change of variable or chain rule of differentiation in case of partial derivative. U is a function of RNS, RNS are function of x and y. So del u by del x via RNS we have to go. So del u by del r by del x plus del u by del s by del x. Finally with respect to x. Now similarly del u by del y will be del u by del r by del y plus del u by del s by del y. U is a function of RNS, two terms, that's why. Okay, but this rule have proof. Surely it has proof, but we are not proving, we are just using the rule. Now if u is a function of three variables, say rs theta, u is a function of two variables, we have seen here rs, u is a function of three variables rs theta, where rs theta are all three functions of xyz, they are also functions of xyz. In that case, what is del u by del x? Ultimately u is a function of xyz, so del u by del x will be del u by del r, here r, into del r by del x plus del u by del s, because of here s is there, into del s by del x plus del u by del theta into del theta by del x. Okay, Here we note that the number of terms in RHS depends on the number of variables in F. In F there are 3 variables, that's why 3 terms. It is not that it is 3 del u by del x. It is del u by del x. Here it is del u by del x with 2 terms because F has 2 variables under it. And here F has 3 variables under it, so 3 terms. Okay. Similarly, del u by del y will be del u by del r by del y, plus del u by del s by del y, plus del u by del theta by del y. Del u by del z will be del u by del r by del z, del u by del s by del z, del u by del theta by del z, finally with respect to z. So this is the chain rule of differentiation or change of variable rule in case of function of 3 variables. Now another concept, total derivative and total differential. If u is a function of x and y, 2 variables, is a differentiable function of x and y, where x is a function of single variable t, y is a function of single variable t, x equal to phi t and y equal to psi t are differentiable functions of single variable t. Then ultimately u is a differentiable function of t. If we put x equal to phi t, y equal to psi t, then we get u is a function of t. So ultimately u is a differentiable function of t. So we can talk of ordinary derivative du by dt. Instead of del u by del t, it is du by dt because u is ultimately a function of single variable. So, and this du by dt is called actually total derivative of u, and it is given by the formula is du by dt. Here it is not del u by del t. Du by dt is del u by del x into dx by dt plus del u by del y into dy by dt. See mixture. It is partial derivative, it is ordinary derivative. It is partial derivative, it is ordinary derivative. Because x is a function of single variable, so straight d, dx by dt. Y is a function of single variable, straight d, dy by dt. And u is a function of 2 variables x and y, so you cannot use the symbol du by dx. That's why it is del u by del x, del u by del y. So this is also a rule, we are not proving, it has proof. And also du equal to, if we multiply both sides by dt, it will be du and del u by del x into dx plus del u by del y into dy. This is called total differential of u. Total differential of u. Here total word is used only to distinguish it from partial. Okay, total derivative du by dt, not partial. Now if u equal to f of xyz, where all xyz are functions of single variable t, then see there will be 3 terms in the right side. Du by dt or total derivative del u by del x dx by dt plus del u by del y dy by dt plus del u by del z into dz by dt, because f has 3 variables under it, so 3 terms. And as before, du will be del u by del x into dx plus del u by del y into dy plus del u by del z into dz. This is total differential of u. Okay. Now one note, if u equal to f of x plus ay, means u is a function of x plus ay. You see here x plus ay is a single thing, single quantity. You can call it f of r. Then what will be del u by del x? F of r, so it will be f dash r. That's why you use the notation dash. Dash is only for single variable function. Here x plus ay is a single quantity. So f dash x plus ay you can write into del r by del x, if we consider this as r, but x plus ay, derivative of x plus ay with respect to x will be 1, so not written. But if we differentiate with respect to y, say del u by del y, then it will be f dash x plus ay, surely. But into derivative of this x plus ay with respect to y, partial derivative of x plus ay with respect to y will be a. X is constant, so answer is that's why a is there. Oh, okay. This is just an introduction to partial derivative, and more about this will be taught in that class, partial derivative class, and examples will be done. But we shall need the concept while solving exact differential equation, testing whether differential equation is exact or not. That's why I have discussed this partial derivative concept. And thank you today for today. Okay.